to look at the difference between a weak and strong acid and how that relates to the pH of a solution. This year, we're going to focus a little bit more on the qualitative aspects of this, and then next year we'll do a lot more with the quantitative side. So when you have concentration, that is definitely a measure of how much solute is dissolved in a solvent, usually water, and specifically for acids and bases, definitely water. There is a difference in the concentration. So 1 molar hydrochloric acid, which is what we often use in the lab, is not so bad. If you got it on your hand, maybe you'd notice, you'd have to wash it off. It wouldn't be that big of a deal. The 12 molar hydrochloric acid that comes from the supplier that I have to dilute is, when I open the bottle, it looks like it's smoking, like it's much, much more reactive. So yes, concentration plays a role for sure, but also the strength. So when you have a strong acid or a weak acid or a strong base or weak base, it has to do with ionization. What percentage of an acid or base dissociates into ions when in an aqueous solution? Okay, so we'll start with acids. So acids, of course, whether you're talking about an Arrhenius acid or a Bronsted-Lowry proton donor, they are considered to be a source of protons or hydrogen ions. So the more ions produced, the stronger the acid. And a strong acid, we say, dissociates completely, so 100%, into ions when dissolved in water. And so this is going to impact the sort of math that we do next year. It is going to be much, much, much easier to deal with mathematically a strong acid than a weak acid. So similar to the dissociation equations we wrote in the Stoichkov solutions lesson, that's essentially what you can do here. If, say, you have hydrochloric acid, its concentration, if it's 2 molar or moles per liter, if you like that better, and then it dissociates into H plus and Cl minus, this reaction is 100%. So that means that if the HCl is 2 molar, because these have a coefficient of 1, their concentration is also 2 molar. So that kind of thing. That's what we'll need next year. So not too bad. One of the other things about it is when you have a stronger acid, then that means its conjugate base is a lot weaker. So that means that in the reverse direction, the conjugate is not going to be a very good proton acceptor. And again, that'll be more important mathematically when we do a different kind of math called equilibrium and ice tables next year. Okay, so strong acids, again, they react completely with water. So I wrote a really simplified version of the HCl but you can write this one here. So you have HCl dissolving in water, and here is the hydronium ion. So the HCl is the acid because it's a donor. That means water is the base because it's an acceptor. So if it's an acceptor, then it goes from 2 hydrogens to 3. And then the HCl has obviously given away its hydrogen and it doesn't have one anymore on this side. Okay? So it is a good conductor of electricity because of the complete dissociation into ions in solution. So once we talk about weak acids, I'll show you a video trying to demonstrate that. So like I said, I've never seen solid hydrogen chloride. Only acids or water loving, strong acids, are water loving, they dissociate so readily that it will completely dissociate into ions. Another example is nitric acid, HNO3. And nitric acid is a very strong acid. Next year, again, we'll talk about the strength, what makes the strength difference even in the acids, strong acids. So nitric acid actually has to be stored in a different cupboard than the other acids. It's so reactive. And again, it's gonna be the source or the donor of the proton, and the water will be the base or the acceptor to become the hydronium ion, and then there's that nitrate ion. So all of the HNO3 dissociates into ions, and the nitrate ion is a very weak conjugate base. So if we were in class, then you would have to memorize these strong acids. Now, some of them we've already talked about, like the sulfuric acid and the perchloric acid and nitric acid. They were part of the naming acids that we did in the second unit. And then hydrochloric acid, of course, we deal with all the time. Hydrobromic, and then hydroiodic. You could do hydrofluoric, but it's a little bit weaker. But those are strong acids. And then perchloric acid is the strongest acid. It has the maximum number of oxygens, and the chlorine ion or chloride ion makes it a very strong acid. In fact, in all my years as a teacher, working in a lab, being a TA, I've never actually used or seen perchloric acid. That's how strong it is. Okay, so weak acids, they do not react completely in solution. So you only get about 1% of the acid dissociating. So that means that the hydrogen ion concentration is always less than the acid concentration. Always, always, always. So next year, when you have a weak acid, that is going to make the math we have to do, the quantitative analysis, a little bit trickier. Okay, so it is a poor conductor of electricity because you don't have a lot of ions. So you'll see that in a second. So this is acetic acid or vinegar, a very common weak acid. And it dissociates. It's a source of the proton. So this proton then will go to water, similar to hydrochloric acid. But then it's not this. It's not 1-to-1. So you couldn't say if this was 2 moles per liter like we did with the HCl. That does not mean that this is 2 moles per liter. That is not true, because it's not a 100% complete reaction, and that is a very big deal. So the way that we're going to deal with it, you'll notice here this arrow is actually going in both directions. So what that means is this reaction can go forward, where the acetic acid and the water are the reactants, and it can actually go backwards or reverse as well, where the acetate and the hydronium ion are actually considered to be the reactants. So we're going to spend almost 3 units doing this math for equilibrium or reversible equations, and that is a huge part of grade 12. So now this, and one of the things about it is related to this, when you have a strong acid, its conjugate base is very weak. However, this acetic acid, which is a weak acid, then its conjugate base, this acetate ion, is not bad. It's a legitimate proton acceptor. So that is one of the differences, again, that we'll talk about next year. So just for a second, I'm just going to show you maybe this video. So there's not going to be any sound. Hopefully it's going to work. Okay, so hopefully you can see that this guy has it's like a conductivity apparatus. So there's a light bulb and 2 prongs with an incomplete circuit. So he's going to take a strong acid and in that solution, and he is going to put the electrodes in the acid, and it's going to complete the circuit. So notice the light bulb, the intensity of the light. So very, very bright. I don't know why he keeps moving it up and down, but when he puts the acid, there we go, the light bulb is very bright. That is a strong acid solution, because there is so many ions in that solution. Then the path provided for the electricity is really great. So then the circuit is more complete. You're getting more electrons, volts, and the bulb is brighter. Whereas now he's going to use a weak solution, and when he completes the circuit with it, you're going to see it you can barely see the filament in the light bulb glowing. all pomp and circumstance here. There we go. So you can hardly see it's the filament itself is barely glowing. The light bulb hardly is glowing at all. So there is way less, 100 versus 1% of ions in that solution when it's a weak substance. So you do not get as much electricity being passed through. Okay, so strong and weak bases are very similar, like they follow the same pattern of dissociation. But again, this time is what's the concentration of OH ions produced instead of H plus. So the more ions, the stronger the base. And again, strong bases, we say they completely dissociate into water or 100%. And the stronger the base, the weaker its conjugate acid. So similar to what we've talked about before. And again, strong bases completely dissociate in water. They produce something that's positive, and then the hydroxide ions, and they will be a good conductor of electricity as well, because you get 100% dissociation in solution. So the most common one we use is NaOH. So 100% reaction, and you get the cation, which is the metal sodium ion, and then the base. Strong bases, even though there's a list here, they're actually much easier to recognize, because you'll remember from the acid and base theories, if it has OH in its formula, it's considered to be a strong base. So sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, magnesium hydroxide, these are all very common bases. Weak bases, again, do not react completely. Only about 1% of the base dissociates, and the hydroxide ion concentration is always less than the base concentration. And again, it's going to be a poor conductor. So this is ammonia. Ammonia is a common weak base. Reacts with water. Again, you can see the reversibility in that arrow. So this time now it's a base, so it's an acceptor. So it changes from NH3 to NH4. And then this NH4 now becomes the conjugate acid to the NH3, and it is a legitimate source of protons. So even though so there's reversibility in the reaction, the ammonium or NH4 plus and the OH are able to react. So again, we're gonna quantitatively deal with this in grade 12. All right, so the pH scale is the P stands for power of. So it's the power of the hydrogen ions. And we use the pH scale as a measure of how acidic or basic a solution is. In a practical way, we say that the pH is a numerical scale ranging from 0 to 14. I'm going to write the word practical. So if you're testing the pH of your pool, the pH scale in the textbook, the homework questions, there's lists like blood, coffee, milk, those kinds of things. You would want to know their pH. So we're going to talk about the math next year. So to calculate this, it's actually negative log of the hydrogen ion concentration. And so those of you that haven't taken grade 12 functions yet haven't dealt with logs. So we'll do that math next year. Okay, so you can do solutions, you can calculate a pH below 0, but that would be a solution like 2 molar nitric acid. So if you have 2 molar nitric acid in your home, then you have some questions to answer. Okay, so this is a practical scale. I want to measure the pH of my hot tub, my pool water, and know whether or not, it's too acidic or too basic. Okay, so a logarithmic scale means that it's not linear. And so the increase in 1 unit of pH is a 10-fold change in how acidic or basic a solution is. So when you have something like lemon juice, which has a pH of 2, and then pop has a pH of 3, then that's actually a jump of 10. So sometimes, or if you look at the solutions, I kind of draw a number line. So 2 to 3 is a jump of 10. Let's say we were going to go to 5. Okay, so we're going 2, 3, 4. That's a jump of 10. And 5, that's a jump of 10. So 5, or sorry, 2 is more acidic. So 2 is 10 times 10 times 10, which is 1,000 times more acidic. Okay, so that's the kind of math that you're going to do for this section. So if you happen to look at the solutions, I literally will draw these jumps and then just multiply them together. So 10 times 10 times 10. So those of you that are into math, if you've ever looked up graph paper, then you'll see like equal grids, and then you'll see something called special graph paper called logarithmic graph paper. So it helps to the spacing between the grid spaces is not equal, so that it sort of takes the tenfold jump and actually makes it into a linear line. So a logarithmic scale is exponential, so it's not a straight line. So that sort of complicates things like trying to calculate the rate of change, which is slope and all that kind of stuff. So but for our purposes, you just look at how many units you jump. So if the question asks you, like there's a pH scale in the textbook, a pH scale with substances. So you just look at how many jumps, how much more acidic is lemon juice than pop, or lemon juice than coffee, whatever the question says. Oh, I wrote it down here. So yeah, so this will be in grade 12. We're going to do this. We're going to use the formula to calculate the pH if you know the hydrogen ion concentration. So in an acidic solution, hydrogen ions are greater than hydroxide. When you see square brackets, that means concentration. I don't know if we've seen that before. So pH range is 0 to 6.9. Basic solutions, now the hydroxide ion concentration is greater, which is 7.1 to 14. So base, hydroxide, acid, hydrogen. And then neutral solutions, the concentrations are equal and the pH is 7. Okay, so take a look at the questions, give them a try. One more lesson in this section. Thank you.